Now we're going to begin talking about something called a string. And this is actually a pretty important piece of terminology. So a string is a way of storing text in the C language. The key here is it means something extremely specific. So in this course, when we say string, we are always referring to something called a null terminated string. And I'll talk about that in over the next few minutes, well, over this whole video, I guess. And it comes down to the fact that we can store a sequence of characters with an array. So we know that already. If we want to store the text hello world, I could just make an array and then set each element of the array to be one character. We know that we can store single characters and values, and that we can use arrays to create sequences of values. But there's a problem with that. And the problem is, if you think about all of the different ways that we work with text, so I might go through a large piece of text, extract every single word. I might take a bunch of words and combine them together with spaces to form a larger piece of text. Each word might have a different length, and the ultimate resulting piece of text, I guess its length, if I chain together a bunch of words, the length of the result depends on the length of each word. And you might realize that if we work with arrays the way we've been doing, which is every time I create an array, I have to remember the size and then pass the size into any functions that need it, that's going to be a huge mess because it's going to require me to keep all this extra bookkeeping. And so there is another option. So we know already in C, there's no magic to give you the size of an array. There's no way of doing that. If you need the size of an array to persist, you have to keep track of it. But there are lots of ways of keeping track of it. The one we've been using so far is pretty simple. We create an array, it's got size 5 or something, and then we keep track in a variable that it has size 5. And we pass that around the program and everybody knows what the size is. But another option would be to keep track of the size inside of the array. And I'm going to show that off, and then I'm going to explain why that isn't an option in general, but it's a great option for strings of text. So the idea is what we do is we create an array, and so I'm going to create an array to store the text hello world, and I'm going to really hope that I can draw sort of well. All right, so there we go, HELLO space WORLD. And you might notice the array is one index longer than I need it to be. This index here will contain a space, and I will adopt the convention that if I leave it blank, that means there is a space there. But the problem is, whenever I hand over an array to a function or anything else, all the function gets is this pointer to the beginning of it. And I'm going to make this ultimately an array of type char. The way that anybody who works with this array knows how many elements the array has is that I somehow have to communicate the size of the array. Usually, we've seen on assignment 4, I just say the array has size 11. There we go. Problem solved. You know the size. But I just explained that that's really cumbersome for text. We don't want to have to keep track of the size of every single piece of text we work with. But there is another option. We know that not every value of type char represents an actual character. There are 256 possible char values because char has values between, the range of char is -128 to 127. There are 256 possibilities in there, but not all of them are representing actual letters or numbers or symbols. A lot of them are unused. So why don't we choose one to represent end of string? And we have that. We have a special character. I'm always going to write it as \0. It turns out that the numerical value of \0 is unsurprisingly the value 0. But I think it's really important that we refer to it as the character \0 to keep track that it's really meant to represent the end of a string of text. We call this thing a null terminator. And we'll see that the word null has a lot of meanings, and they're similar, but they're not actually the same. So the null terminator is the character, single quotes, \0. We write it like this, in single quotes, just like anything else. And the convention that we have adopted in C, that all C programmers adopt, and the standard library also adopts, is that if ever I refer to something as being a string, then it is guaranteed after all the text in the string, there will be a null terminator. So in this course, if you construct something called a string with no null terminator, that is considered incorrect. And you would be marked down on an exam, often quite heavily, because without a null terminator, as we'll see soon, the string is essentially invalid. It's impossible to know where it ends. So let's begin by constructing it. So I'm going to create a character array S1. If I count how many indices I actually need here, okay, 0, 1, 2, 3, 4. Okay, so I guess because I have to include that null terminator at the end of my array, I need this to have size 12. Okay, and it equals, okay, character uppercase H, character E, character L, character O, character space, character W, oops, the character O, character R, character L, character D, and then finally, we'll write it like this, that null terminator. So I've just constructed this array S1 now matches my diagram, and I've constructed the array element by element using these single quotes, setting each element to be its corresponding character. And you could see this is painful. If I want to store a whole sentence, this is going to be a complete nightmare. Not only because I have to keep typing, but it's really easy to lose track of where the letters are and where the commas and single quotes are as well. Also, because I expect in every string in C to have that null terminator, I have to put it in manually, which means I could forget it. But I want to make my next point before I explain that further about how the null terminator actually works, which is I have this string of text. Let's print it out using printf. So printf has a specifier, %s. I'm going to say the string is, then I'll print it out using %s. If you provide something with %s to be printed with %s with printf, printf expects a string. And remember that string means a null terminated C string, which means it's the pointer to the beginning of an array. So when I give the name S1, I'm giving printf directions to where my array begins. And when printf tries to print the string, what it does is it starts at the beginning of the array and it walks through step by step, printing each character, H-E-L-L-O space W-O-R-L, and printf stops as soon as it hits that null terminator. The null terminator is not considered to be part of the string, but it's expected to always be at the end of every string. So it's not part of the text itself, but it is used to indicate the end of the string of text. So we'll try running this and see what we think. All right, so the string is hello world. And printf stops because it sees that null terminator at the end. It doesn't print the null terminator, it stops as soon as it sees it. So when you construct a string in C, it must have a null terminator, always. But on the other hand, we do not want to construct strings like this. This is a nightmare. We can because a string is just an array. It's an array of type char with a null terminator at the end. There is no difference between it and any other array besides the fact that we expect that null terminator to be there. And so there are some shorthands, some syntactic sugar we can use, but you could, I guess, if you want to, create every string ever using this notation. But let's talk about the shorthands. So first, there is a special kind of initializer just for strings. Remember that the null terminator, the requirement that we have it, that is a social convention. That's something that the C language doesn't require. You can create arrays of type char that just contain numbers because char is a numerical type. If you choose to create a string, it's expected there's a null terminator. And the C language embraces that. We'll see later that the standard library has functions for working with null terminated strings. And it turns out that the language provides a special kind of array initializer just for strings. I want to make one note on my other initializer. You might remember I don't have to put the number 12 here because the language will see my initializer and know to create an array of exactly that size, which is 12. I'm going to do the same thing here. I'm going to create an array and I'm going to initialize it, but I'm not going to use the curly brackets. I'm going to use double quotes. And I'm not going to put a null terminator at the end. And we've been using double quotes all semester. And an early question I got was, hey, printf is a function, right? Then what's the type of this first argument? And the answer is, it's a string. The thing you put in double quotes is a string. It's exactly the same thing being created here. When you use double quotes to initialize a character array in C, you are asking the compiler to make you a string. And so the value of S2 is going to be an array of size 12. 5 characters for this, 5 characters for this, a character for the space, plus a character for the null terminator. When you use double quotes, the compiler puts in a null terminator for you, guaranteed. Double quotes are for the specific use of creating null terminated strings. They're not for single characters, that's what single quotes are for. They are specifically for creating arrays of char with a null terminator at the end. So we can use this. And frankly, we really should use this. This initializer is a nightmare for this purpose. It's great for regular arrays, but it really isn't very useful for arrays of characters. Okay, so the next question. S1 and S2 both contain the same thing, so I'm going to talk about S1 for this question. I have this string here. How long is it? What is the length of the string? We know how many elements are in the array. The array has 12 elements, but what is the length of the string? And the answer is, in my opinion, the string has 11 characters. 5 for the first word, hello, a space, that brings us to 6. 5 more, that's 11. It's true that the array needs 12 elements, but only 11 of those elements actually go towards the string of text. If I'm talking about text with somebody else, and I'm saying, here's a string of text, and I'm not talking about C programming, they wouldn't know what a null terminator is. They don't care. The null terminator is part of the machinery that lets us represent the text, not part of the text itself. And so it's reasonable to say the length of this string is 11. Even though it's stored in an array of 12 elements. And that's also something we have to agree upon for this course. And when I say we have to agree, what I mean is I'm forcing that agreement upon everybody. The length of the string is 11. I mentioned earlier in the course that sometimes 2 plus 2 equals 5. This might be one of those times. And so if ever I talk about the length of a string, I'm talking about the length of the actual data it stores, not the extra machinery, like the null terminator, that I use to help represent it. So the length of the string is 11, and an early problem that we're going to have to think about is, how do I find the length of a string? If all you give me is directions to the beginning, how do I find the length of the string? Keeping in mind that unlike a lot of other array questions, you wouldn't be telling me the size of the array. You'd expect me to figure that out myself. And the answer is, of course, I would go figure out where the null terminator is and then work my way backwards from there. Okay, so that's one thing. But let's talk about working with strings a bit more. So modify the string at S1 to change the character W, that would be this character here, the one at index 6, to be the character X. Okay, I can do that. This is a very basic array exercise if you think about it. So S1 at index 6 equals the character. Notice I'm using single quotes because the type of S1 sub 6 is char. Double quotes are only used for initializing a character array. This is a single character. Okay, so I'll change it to X. Let's print it out again. The string is now, actually I'll just put the string is so it lines up, and then I'll print out S1. We'll ignore that warning. And we can see here I've changed this to be hello and then an X instead of a W. Okay, no big deal. Of course, I can change individual characters. All I'm doing is changing one of the elements of an array. Okay, next. Modify the string S1 to replace the O. That would be the one here at index 7. That's a weird looking 7. There we go. It's a bit more confident 7 now. Change the character at index 7 to be the null terminator. And the reason I want to do this example is, actually before I do it, I want to rewrite this. Let's print the string out inside of square brackets, or inside of, well, square brackets are fine, just to make sure we can see every single character that it thinks is in the string. Okay, so we can see here the contents of the string are this and nothing else. There's no spaces at the end, no spaces at the beginning, just the string itself. Okay, let's modify the contents of the string to replace index 7 with that null terminator. Okay, so I'm going to update my diagram here. So first, this now contains the letter X, and this now contains \0, the null terminator. And so we'll try printing it out again. I'm just going to copy and paste this. And we can see, because of the way that the null terminator works, as soon as anybody working with a string hits a null terminator, the string is over in their eyes. They have no way of knowing how big the original array was. All they know is, here's where it starts, keep walking until you see a null terminator. And so the printf function is no different. It starts by printing HELLO space X, and then it's done. It stops. It hits that null terminator. It has no reason to believe there is anything left afterwards. And to be clear, even if you thought, hey, maybe the string didn't actually end, maybe that null terminator is bogus, if you look afterwards, you're getting yourself into trouble, because what if the array actually did end here? If it did, and you walk one step too far, you're in unknown territory, and that could cause some sort of memory issue. So we have the rules for a reason. And that means one sort of shortcut, if you want to truncate a string, if you want to cut it off early, is just to add a null terminator in the middle, because that'll fool any function working with it into thinking the string is actually over. Okay, let's talk about writing some loops that work with strings. And you'll notice that just like there's this characteristic style of loop for working with arrays, the one I typically write is I equals 0, I is less than the size, I plus plus, there are also sort of characteristic loops for working with strings. And I want to show off two different ways of handling this. The key is I want to work with this string s2 that I created above because S1 has been modified. I'm actually going to cheat a little bit here, and I'm going to pretend, because we're now done with S1, and because drawing these things on a screen is so painful, I'm going to say, here's my diagram for S2. It looks like this, and then we'll just pretend we never heard of S1 before. Okay, I want to work with S2. What I want to do is I want to loop through it, and I want to count the number of lowercase letters. I'm going to use the isLower function to do that, and so I guess I'm going to need some count variable. Lowercase count equals 0. Okay, and then when I'm done, I'm going to print out a number of lowercase letters, and then I'll print out my lowercase count. So the question is, how do I get to this answer? What I need to do is I need to walk through the string s2, and I need to count every character. I need to, for each character, ask the question, is this character lowercase? So really what I'm asking is, how do I loop over a string? And there are two ways of doing it. There's I think the sort of pure way, which works only with a single index at a time and stops when it hits the null terminator, or we could reduce this back down to a sort of general array problem by figuring out how long the array is and then just working with it like it's any other kind of array. I'm going to start with the first approach. I'm going to call this the pure string approach. Okay, so what I'm going to do is I'm going to initialize an index, so int I, I'm going to start my index at 0. And I'm going to use a while loop for this example, but actually in practice I'd probably use a for loop for this. Personally, I like for loops for array things. And what I'm going to do is I'm going to keep walking as long as s2 at index I is not equal to my null terminator. I don't know how long a string is. In this example, obviously I do because it's on my diagram. But in general, if we work with strings, we shouldn't assume anything about their length. The length of a string is simply how far can you get until you hit a null terminator. So I'm going to say, while the character at this index isn't the null terminator, then I'm going to ask the question, if this character is lowercase, if is lower of the current character, then I'm going to add one to my count. We know that is lower returns true or false, so I can just stick it directly inside an if statement. And then outside my if statement, to make some progress, my incrementation will just be I++. I just walk along to the next index. So to mock that up on the diagram, what I want to do is I'm going to start at index 0. I'm going to ask the question, is this a null terminator? Answer is no. Okay, then I ask the question, is this lowercase? Also no. So I move along. Is this a null terminator? No. Is it lowercase? Yes. So I add one to my count. And I keep going. Is it a null terminator? No. Is it lowercase? Yes. And eventually, if I walk along like this long enough, I will hit a null terminator. If you gave me a valid string, it's guaranteed to have a null terminator somewhere. Maybe index 5, maybe index 11, maybe index 9000. Who cares? It will have one. Every string is required to, or it's not valid. And when I do, the loop ends. Okay, so we'll start by modeling that solution there. I guess I'll need to count. I'll need to actually verify my answer. So it claims that there are 8 lowercase letters, and I'm counting 4 in the first word, 4 in the second word. The space doesn't count, so yes, 8 sounds like the right answer. Now, suppose that you stare at this and you say, okay, I guess I sort of buy that, but you don't think you'd want to write it this way yourself. Maybe you believe what's happening if you trace it, but it doesn't make sense if you try and write it yourself. What are your other options? Okay, so one option is, can you figure out the length of the string? And we'll see later there's actually a library function that tells you this. So that makes your life a lot easier. But I'm going to compute the length of the string by hand using the same style of loop, and then demonstrate, once you know the length of the string, how easy it is to just loop over the string like it's a regular array. So int string length equals 0. So what I want to do here is figure out what is the length of the string. In other words, how many characters are actually part of the text in the string, up to but not including that null terminator. And what I'm going to do basically is just wander along. I guess I'll create my index I again. And you might notice, if you're watching, that actually you don't need both of these variables. They happen to refer to the same thing. But like in the array examples from last week, using two variables, if it means things make more sense, is a good idea. So I walk along while s2 of I is not equal to a null terminator. I just increment I, and I increment my string length. And maybe you can prove to yourself that actually I and string length will always be equal. But for the sake of things being clear, let's keep them separate. Okay, so at this point, string length refers, is the size, better say length of the string. So suppose you know the length of a string, either because you've computed it by hand or because you've called some function in the library to do it for you. And in the video, if you scroll down a bit, you'll see that there actually is a very useful standard library function that gives you the length of a string. And that means you don't have to write this kind of loop very often. And if you do, maybe you just have to write it to find the length. You can then loop over the I'm going to use a different index. I'll use a for loop for this. You can then loop over the string just like you would loop over any other array, because you now know its size, and you can write the standard issue array loop for it. So j is equal to 0, j is less than string length, j++. Okay, and then I ask the question, if is lower of s2 sub j, then increment my lowercase count. And I'm going to go verify that I didn't comment out the declaration of lowercase count. No, there it is. It's up there. All right. So if I already know the length of a string and I want to do something that involves iterating over it, I can just write the typical array-style loop, which means if you don't like this style of loop, you can avoid writing it in a lot of cases. But I really recommend when you work with strings that you get used to this style, because it actually can often result in cleaner-looking algorithms than having to go find the length and then work with the length. But as usual in this course, it's sort of up to you. It's about writing code that works, that makes sense to you. And there we have it. So we've found two different styles of loop that will count the number of lowercase letters. We've noticed that if you want to use the array style loop, you do have to find the length somehow, either by writing the other kind of loop, which is a bit redundant, or as we'll see, by getting it from some other source, like some kind of library function. And the key is, if I give you a string, you don't know how long it is until you go looking for that null terminator. And if your job is to create a string, it isn't a string until you've put a null terminator at the end.